All right, people. So we have 5 more lectures left, and I'm excited to tell you about scaling over the next 3 lectures. We've had a lot of this parallel stuff, but that is not where we are now. We are. So, all right. So first of all, we have a game. So this is going to go over a few lectures. Here's a bag of chocolate-coated almonds. Please regard the bag. Right? Looking at the bag. Right. So the plan with this bag is to eat it. Now, to getting to eat, I trust you. So the idea is this. It's fun. So the winner is going to be the person who gets the closest estimate by percentage on average, and I'm going to give you a few things to estimate. So the first one is, and I've written this in a bit of a funny way. So the first one is how much does this weigh according to my scales at home with me using them? How much does this weigh to the nearest? So that's a factor. I tried it, but it's a digital one. To the nearest quarter of an ounce. So I'm going to hand this around. And we'll do this through the lecture. Why don't we do this? So, put your name, write it down, and we'll go in the same order if you can every time. But I want you to write it down now. I want you to get an estimate now before you see anyone else's. Okay? So, that's it. So, I want you to write it. What's it? Absolutely not. You're not allowed to watch anyone else's stuff. You need to write it down now, and when it comes around, there's no changing. We'll get to that. Okay? No changes. Whatever it was. No, please write down what you, just write down a guess. You're trying to win chocolate. Chocolate-covered almonds. Chocolate-covered almonds. Very you have to think about it. How thick is the chocolate?
Can you try it in the hour?
No.
Can you give it a toss?
We're done. We're done. That was it. That's it. So I want you to write that down. I want you to write down. Get out a piece of paper and write these things down, and you have to hold firm to them, right? When it comes around, you just fill in your answer. Don't look at anyone else's. This is... Okay, no looking things up online. No magic rectangles. Don't use your magic rectangles. Use your magic rectangles. So here's the next thing you have to estimate is how many almonds are in the bag. So we have 4 things to estimate, and you have to get as close as you can on average sort of. So write those things down. So that's coming around. Chocolate almonds. We'll have a number for those. Have a number for this. What's the bulk item number? The chocolate coated almonds at City Market. I'll get cotton kid. Alright, so sorry, it's a troll. Just guess, write down, you have to have it written down before it comes over to you, okay? So that's that one. And then the last one for you is, what's the volume of Neptune in cubic miles? So, estimate that. Again, have your numbers, have all those 4 numbers down before this piece of paper. So there's a couple of lectures from now when we'll revisit this situation, alright? I don't want you guys to get your numbers out. Yeah? Cubic volume? Neptune? Got it? Good. Alright. So you might want to be quick enough. I mean, how hard can that be? Alright. So, while you're thinking about that is a set of slides we'll revisit. Yes, no, I'm on document camera. Okay, I'm not even going to use it. Yeah, so the slides are up, so you watch this. So CLA appeared in this set of slides. We're now into scaling, so it's elementary scaling. I'll tell you what that means. There's a little connection here at the end when we get to it. Can you put Oh yeah, so, well, they're coming around, but it's the weight. So it's the weight to the nearest quarter of an ounce, number of chocolate coated almonds, according to my count on a cookie tray, and the bulk item number at City Market when one purchases these sort of things. They're not organic, I'm sorry. And what's the volume of Neptune in cubic meters? Just do what you can. All right, so this appeared at the end, right? So next up, 1/12, the difference between good and evil, 2/3, 3/4 star and death by fractions, a Truthicide department investigation. So there's going to be, this is a, okay people, no talking, it's an independent thing. People. It's an independent. Okay. There are other humans here. They're here. Okay. So, death by fractions, alright? So, 1/12. Apparently this matters a lot. It's sometimes called the Judas fraction. It's the devil's number, all those sorts of things. That's this one. Alright. So there's the cricket score, we'll come back to that later on. I do have papers to return, we can do that at the end. Oh yeah, Seth. Canbar is talking on Friday. You should come to this, this will be great. Yeah, Can, it's 3 to 4. It's the Davis Auditorium, which is not the Davis Center, it's at Fletcher Island. So this guy is fantastic. You should really, so 3 problems in social computing. Very, very interesting. He's at the Media Lab at MIT. Used to work for Google. He's done a lot of great stuff. He and a colleague of his helped us get going by inspiration on our work on happiness, actually. Jonathan Harris. So, alright, so he's going to be great. We're excited to have him on. And I think I will start talking about these other things. Alright, so there's a lot to talk about here. And as I've hinted to, there's this strange history that's still unfolding of people arguing and fighting about 1/12. And they're very upset about it. So I want to talk about scaling in general. Of course, we've done this parallel size distribution business. Yes, we know all about those things. You're sick of it. You should know about it. The statistics of surprise. This is a different story. This is how pieces of aspects of systems scale with them. Right? So if we scale up trees, for example, what's the typical width of a tree versus its height? How does that scale? Is it isometric? We use this word isometric. Do they all look the same if you scale them all down by just turning a knob? Would they all look the same, or do they stretch out in some way? Or tend to kind of become broader, relatively broader in interesting ways. Right? Is the spherical cow assumption a reasonable one for all organisms and so on? So lots of different things. When you think about engines, how does engine size scale? Horsepower and all sorts of things based on the actual mass of the engine. There's lots and lots of different things. Cities, we can think about cities, how many patents a city produces per capita, how much crime there is. Do those things scale? Are they just linearly related? Are they sublinearly related or superlinearly related? Right? So that's what we're going to be going for. It's this word allometry, which we'll get to. And then I want to go through this, as I said, kind of ongoing story. It involves networks, you know all about that. It involves the scaling that we'll talk about. It's river networks, blood networks. Leonardo was perhaps the first person to write down that he thought those things were similar, so it's kind of another story. Very much fractal network sort of things. But somehow they connect into how much energy per unit time organisms use. That's the idea, right? And that's a big deal for biology, ecology, life in general, you know, on this planet, other planets. How things fit together in ecosystems, and that's what this 12 is. Okay, so there's often a scale. I mean, you have systems of many different sizes, but they're of the same kind, right? So you have cities. We can think about little towns going out through cities of different sizes, and we can say, all right, well, let's measure some pieces of that. Or organisms, right? We're vertebrates, all the same design, apparently except for we're all vertebrates running around with the same number of, right? Giraffe has the same number of cervical vertebrae as we do, and sexual vertebrae and so on. So, except apparently for one of the sloths has a few more. It's like Brains, all names. But you know, right, we have those same kind of body plans. We all keep ourselves warm, various different ways. So how does that work? All right, so I'm going to give you some examples. How to measure these things. This is different to measuring the scale of it. It's really dropping off. It's a bit different actually, because usually there's some relationships there, but usually we've got things growing with each other. Not always, but usually we have things growing with each other, and that's a different kind of measurement. Right, number of species is a function of area. That's a good one. Anyway, I'll give you lots of examples. All right, Moore's law is another one. I have to put that. Okay, so there are millions of this. All right, so we're going to get to these two big examples that are connected together. Very interesting way. It's a network story again. River networks. This is the global scale river networks I'm talking about, not just little guys. Right? We're talking about continental scale, Mississippi, the Nile, Amazon. Really, the big structures you see from space. And then we're all full of these blood networks, right? That are distributing nutrients to our bodies all the time. So we'll have that as well. All right, and then we have Truthicide. So there's been, maybe it's Truthicide, so we have to figure that out. I'll tell you what I think it is, but this is still an ongoing argument. It's something to do with this word allometry. All right, so we know all about these relationships. Usually we've set it up so that there's a probability of x, and it's x to the minus gamma. But this may not be positive, but as I said, we'll be looking at a little more at ones that are growing. And they're not, so it's not a probability story anymore, right? There are two things you might measure about a system. Of course, we said it's a scaling exponent, we have about exponents, and we have our prefactor. So it's the same kind of story, but right? It's not necessarily going to be a dependent variable. When we come to organisms, we might say that mass is a big deal. We might say mass is the elephant in the room, so to speak, probably for organisms, right? Once you've got your mass fixed, then there are lots of other things that are dictated by within some reasonable variation. You might say the same about cities, right? But again, we'll see lots of variation. I think so. I did an analysis of this at some point. So we talk about agglomerations for cities, right? So that just means if you look at it from space, you know, Boston has 5 or 6 million people. It's not the center of Boston, right? It's this thing. It's this functioning thing of people moving in and out. There are certainly political boundaries, but from a functional point of view, it's this maybe 5 or 6 million people. And you can look at the area that they span, right? And so the area they span can vary by 2 orders of magnitude as a function. So there's really a massive amount of variation. So as you go up through population of city and you plot area on this axis, log, of course, because we love those things, 2 orders of magnitude. You see this huge scale. Very, very different systems we can create with cities. Okay. I haven't really talked about, we've sort of left the prefactor, but it is a bit of a funny thing. So, it's going to contain, it's not a dimensionless piece, right? This is a very important thing to think about. We write down equations. This is the beautiful Buckingham pi theorem, which you can get you all sorts of things for free by thinking about the dimensions of systems, right? So you can figure out, for example, the radius of the circle. Pretty, very simple things like the radius of the circle must be proportional to its circumference because there's only one scale in that thing. And they both have length. One has to be a function of the other. There's no way you can have whether you measure it in yards or meters or parsecs matter, right? It can't matter. So you have to have dimensionless equations. So these things are a little funny. So imagine you have a length scale of a system varying its volume, right? So this might be trees, for example. Could be the height of trees. We look across many, many trees, we go and measure trees, we climb up the trees, we measure trees. Trees are a bit hard to measure actually, because if you want to get all the branches, that's actually quite a tricky thing. You should have to stick one in an MRI machine, but we can't get it. We actually came up with an idea of tree bots. We should get one guy to do this. Little guys that run around and tell you where they are in space, and then you get a 3D picture of the tree. Ridiculous. Alright, so this guy has to have some dimensions. So if this is in meters, this is going to be meters cubed, it's meters to the 3/4, so that's what's going to happen here. So the dimension of this prefactor has to be the dimension of length divided by the dimension of volume. So in this case, it has a dimension, which is a little funny. Right? All right. Just real quickly. We know these things. They're still linear, right? We still have this story. We love to look for straight lines. We've done this with the decaying distributions. Right? We'll use base 10. I'm going to say it again because we're good people. Right? Any monks who get to 10. Anyway, it is something we made up. It's true. Okay. We have orders of magnitude. All right, good. So here's a. I'm going to show you some pretty controversial examples eventually, but this one is great. Okay, and it's still not completely sort of somewhat, but Sarnowski spoke just as sort of in the SEP campfire, as I said, speaking on Friday. So we had Sarnowski speak a few years ago here. As part of our complex system stuff. You know, he's a superhero in all sorts of things, computer science and neuroscience. So he's done a lot of stuff. But this is often we're looking at brains. So I've tried to get a reasonable one. Maybe you can see if you have any screens. But here's a fit. It's a log space. So it's gray matter versus white matter. So the gray matter is the computational stuff, and the white matter is the wiring, broadly speaking, right? So we have to communicate between the little thinky bits, and they send little signals. Of course, someone has very enjoyably got some brains out and counted those bits up with scales, right? Kitchen scales. And then, so the relationship here is scaling. So this is a log here, it's a little hidden. I've written it down here properly. So the white matter, the volume of white, so it's volume. Volume of white matter is scaling with the volume of grey matter to 1.23. And there's a plus or minus, what do they got? 0.01 is their error. It's a 0.998 regression correlation coefficient. So that's pretty good. You would have some of these things. So there's a cat and a puma, as I would want to say. So elephant, pilot whale, where is a human? Human is floating around in human. So we're pretty thrilled with ourselves, right? But we are on this. We're on this thing. We're not right. We might have a bigger brain for our weight, which we revel in as we get eaten by a tiger. Smartly, you know what you call it. But this structurally, right? We're in the same game. Evolution didn't produce something different from people. Right? We're just on this line. Rabbits there. We have pygmy shrews. So the shrews are the smallest mammal. They're really little guys, like 3 or 4 grams, I think. They're tiny units. So there's a lot of good stuff in here. But clearly, people like shrews. They like hedgehogs to bring them in with their white, coats. A lot of hedgehogs. Lemurs. Kind of bordered here. There's a dwarf bush baby, a flying fox. Really, it's kind of a macabre set. Anyway, all right. Mama said, poor guys. There must be a sloth in here because there is a big cat. Sloths? Maybe. All right, but this is a great scale. That's what I want to say. This is just fantastic. This is the one you put on the T-shirt, right? I like allometric scaling. It's real. Right, it's a hard-working example. So you feel like, you can go on, right? This is from Students of the National Academy of Sciences back in 2000. So let's think, so why is that, right? So the wiring is increasing, right? There's more wiring, more cabling. Which is pretty interesting, right? So the scaling super linearly. We need more, we don't need, it's just that it seems better to have more connection. We'll see that's not really true for cities, right? When you look at electrical wiring, plumbing, roads, and so on, they actually scale sublinearly. So there's a returns to scale, if you like. The returns to scale here, you can appreciate reality TV shows better or something, right? And there's more wiring, so you can, what are we doing with our brains, humans? Right. So let's see, I'll go through a little argument that they put up. Just for fun, so this is a nice little one. There's some sneakiness in here, but we'll see. All right, so we have the volume of grey matter, that's G, volume of white matter. We have cortical thickness, T, so you have, right, hopefully your brain is nice and curvy, wrinkled and so on. But there's a thickness in that scrunched up thing that you have in here. There's a surface area associated with that. And then then they talk about the average length of these cables connecting different regions. And then you have a density of, a density of axons coming into a particular part of the surface. So we can put these things together and see what happens. And you could debate some of this. All right, so here's the first idea. There's some curvature to this thing, but it's not super fractal, right? You can get into trouble with some of this business when you say area times length equals volume. That feels like a good thing to do, right? But it could be that you've got a sponge or something. It all goes to bits when you have fractals. Okay, so but here's the idea that in general, as you go up through scale, so we're starting with the shrew, we're getting to the elephant. The volume of grey matter, the thinky stuff, is proportional to the surface area times the cortical thickness. Okay? So all of these things are growing in interesting ways. So let's get to that. And I think there'll be sort of there's an empirical part that we have to apply to. That's right. Now the white matter, let's see how this works. So there's the surface area, right? And then there's the average length of all these connections between those regions of the brain. So that's the L. And we have a P for the density, right? So P times S gives you the total number of axons through this whole surface. You divide it by 2 because they have 2 ends for each link. And multiply by L. So that gives you something that's sort of maybe a thickness of, oh, that's right, that's right. So this is a volume. So this gives you a volume. Good. Okay? Yeah, your brains are just happening in your brain. So. And then, it's not bad. I mean, so the volume of the grey matter proportional to L cubed. You have to really think about some of this. So if you've got this brain, it's got all these links tying it together, and you're thinking about celebrities and so on with your great brain, then your brain gets bigger as you go up through the shrew up to elephants who are thinking about hay and stuff like that. And then you have the idea that it's reasonable that the total volume of this stuff, it's a bit funny because you've got this brain and it's got all these connections in here. This is a bit of a funny one. That's the idea. Right? So L for these guys, for this scale, roughly all this stuff in here is G. It's three-dimensional, and it's been sliced. So you can mess around with this. This is a nice little exercise. We'll get rid of the S, we get rid of the L, and we'll get this. So I won't go through it, but we get that the white matter is proportional to G to the 4/3 divided by T. So that's 1.33, right? That's a little too much. But it's divided by the cortical thickness. And so then we turn up and we say, well, actually, the thickness of the cortex is growing. That's an observation. I got this right. Yeah. So we're here, and this is an observed thing. So this would need to be explained as well. This is not explained as of the time of this paper, but the cortical thickness is growing as you go up through bigger and bigger animals. There's more computational units through the cortex. If you like, it gets deeper. And it's very, very weak, and that's such a weak scale. But if you put all those things together, don't worry about this piece. But basically, so we have G to the 4/3 divided by T, so that gives us 1.3. So it's pretty good, right? 1.33 minus the 1.1 gets us that observed scale. So it's a little bit of a just so story, a little bit of a back of the envelope. We like those sort of things until we realize that they're beautiful lies. But it's not bad. And certainly, the empirical story is fantastic. Right? Providing that the way we measure the white matter and the grey matter, with our mad scientists, rubber gloves and stuff, provided that was all done in a way that wasn't with error, but lots and lots of measurements. All right, so interesting. So that's how our brains work. There's some funniness in here. You have that the total volume is roughly, they try to deal with this, is really the grey matter plus the white matter. But all of these things seem to be scaling pretty well, right? So there's some errors in there and so on. So white matter is scaling nicely as the whole volume. Grey matter it's almost scaling its volume. There's a 0.995, there's the exponent here, so 1.174. And you can see these are pretty good too. So there's some little nasty details, but you can't really have all these different parallels. Alright, so it's a nasty business. It's a nasty business, but gotta do it. And this is again, let me go back to the graph because it's great. I just want to feel good for a little while before we get into the back things. Okay, so maybe 6 orders of magnitude? Yeah, maybe 5 orders of magnitude. Yeah. It's solid, really good, and it's that many orders of magnitude on the vertical scale as well. All right, good. Exciting. Right. Talked about this, but let's write it down. So 3 orders of magnitude is good. Each variable, that's terrific, right? That's when we start to say we feel like we've got scaling. We can measure it in different ways, and it's pretty solid. I mean, it's just a really complicated, not complicated, but just it's been a bad thing statistically. People have argued about this for a long time. This is not bad if we have 3 or more orders of magnitude. That often happens, but the vertical axis doesn't vary as much. And then we saw this, say, for the electrical grid for the idea that it was a scale-free number, right? It had really, maybe half an order of magnitude. Very bad. Shouldn't do that. Okay. That's very bad. People will do it. I guess I'll let this put you later on. But this is this one is not so good. I'm going to cover this paper later on. It's great. Here's the scale at 0.093. Again, extremely weak. Bad things are happening in this NAS. Dirk Albing is a good friend of mine who's part of this, and look, it's a great paper. But I have to say, this one's a little dubious. First of all, natural log, very naughty, very bad. Because you think, wow, look at all those, all those magnitudes. Gee. So that's not good, because it's hard to compare to other things. But it's very weak, and this has been debated. So let's see what this is walking speed as a function of city size. So walking speed goes up, right? It's, I think there are more measurements, I think it might be double as the highest walking speed. So it's a much more, it's a bit messier, but this is a very weak scale. But this is the idea that the pace of life increases in cities, which is the opposite to what happens with, this is the opposite to what happens with organisms, actually. So bigger and bigger organisms have lower, their heartbeats go down, right? So a mouse is sitting there going berserk with a little ticker, and elephants are boo, boo, right? And in some sense, their individual cells, they're all mammal cells. They're mammal cells, right? They're not, like the elephant cells aren't bigger, they're the same building blocks. But there's less mitochondria in the, from what I understand, in the elephant cell than the mouse. So they're just running at a different time scale. Got to get the mitochondria. Collegiate nationals. All right. Shut up. Okay, so scale invariance, and you see people will say this is, Barabasi will say this sort of thing, and the parallel size distributions. This is the signature of complexity. Maybe. I mean, it's certainly one big aspect. But there are many systems where you move up through scales and things change. We're not carbon atoms, for example. All right. Lots of things can be the same as we scale, right? So the idea is that there's some rescaling that we do, and then the objects look the same. We rescale our elephant, and it looks like a mouse. Right? We have to do bad things to its trunk, but we get it to look like it. And we might get its heart rate to look like a mouse if we rescale things, right? And of course, famously in fractals, we have all sorts of rescaling there that we can do where we make things look the same. And so that's a we'll get to what I mean here. So there's this idea of the object. So this is fractals, geometric shapes, time series. Heart rate again is another, actually there's a lot of fractal stuff in there. We'll talk about random walks, lots of stuff in there. Lots of things. So same can be statistically the same, right? It can be kind of messy, but statistically the same, particular time series. Doesn't have to be exactly the same. And rescaling, what do we do? So we're changing the units of measurement, and what we'd like to do is put them all on the same page, right? Elephant, mouse, giraffe, scale all down. We'd like to scale all our cities, right? So one thing we've been doing recently is looking at how people move around, and this is work that started by Marta Gonzalez, looking at mobile telephones usage, and it's somewhat coarse, but you can see that there's sort of a universal pattern to the way people move around, with some extra details on top, right? So some people have sort of a small range that they move over, some people have a very wide range, wide range, but there's a way of rescaling them so they all match up. So in some sense, people who travel one way a lot, they're just sort of a stretched out version for people who travel short distance. They're not qualitatively different. It's a difference in scale. All right. Little things. Okay. So this guy, let's just get it absolutely right. So we're going to rescale x with an Rx prime, and if we do the right thing with y, we'll rescale it as R to the alpha y prime. That's going to work out for us. So let's just replace y with R alpha times y prime. That's there. We're going to put the x equals Rx prime here. So you'll see what happens here. R to the alpha, those things are going to cancel. Right? We're going to put this R to the alpha on the other side. These pieces cancel. And we get the same equation for these new variables. It's exactly the same equation as we started. And that's what we mean by rescaling. How we rescale them depends, right? So in this case, if alpha is a half up here, and we rescale x, then we have to place some factor in 10, and we have to scale y by a factor 10 and a half, right? So that's this, getting to this idea of what we call non-isometric scaling, right? Non-affine scaling, self-affine scaling, and what we'll call allometric. So you can't do it with other things. So for example, many matrix here has to be this parallel relationship. We can just see it absolutely clearly. So if we put x as Rx prime in here, like we did before, well, there's no way to pull that R out, right? We're kind of stuck inside the exponent. There's no way we can pull it out and say, if we change y by some factor, we could. We can't retrieve the same equation, right? It's changed this lambda up here. It's all the same. We didn't quite do it in the same way. We had the same sort of thing for the size distribution. So we can't get back to it, so the scale matters for exponentials. These guys, we'll talk about this having a characteristic scale, 1 over lambda, and we can see it, right? Once it's x is much greater than that scale, then y is small, and it's large when it's not. There's really a scale. This is another one, so I'll get rid of that. Okay. Very exciting. There is a sinister cabal that might take me out as a result of talking about these things, but I've got to get out there. Okay, so allometry. Freemasons, those guys, right? So, okay, so this is what we would call isometric scaling. Right? Take our tree and we'll just do a little thing on the Mac or whatever it is, like this, on your iPad, or you just dial something and it just goes, scales up. This is not how trees work actually, but this is allometry, so it hasn't really stretched. In fact, it's kind of shrunk this way, right, from scale. So that's it. And if that's happening, and this is of course just two examples, but if this is happening in a robust way, then we talk about a nonlinear scaling, and we use this word allometry, right? So allo means other. That's the source of that. Iso means same. So originally it was about organisms. It comes from biology, talking about body parts, limbs and all sorts of things, and heart rates and so on. But it's this differential growth, particularly say as an organism grows as well. That's another place. So you can have cross scales of different types of organisms, but also how an organism grows as well. So we'll have some examples of that. And actually, it's Huxley and Tissier going back to 1936. Some very unseemly other sort of articles in that nature. I went and found them in the library years ago. We're talking about, I think the paper before was about eugenics. How to do eugenics, right? So, wow, well done, nature. Well done, humans, 1936. All right. I think it's sort of, it was an outgrowth of a mixture of things, but one of them was animal husbandry. Okay, so, very disturbing. Anyway, this was a benign little piece that just said, there are lots of different words for this sort of thing that we see over and over again. We're going to use this, we want to propose this word allometry. Allometry. It's fun to say, allometry. Okay. Not as much fun to say as the word log. That's a different one. Okay. It's the L. Okay, so let's see. So, we've got this business. Yeah, there's a bit of a funny thing that we'll say. So, there will be this kind of scaling where we have a dependent variable and an independent one, and we'll also talk about correlated ones. Okay, so, and you have a different approach to measuring those ones. If one of them is very well measured, the other one's dependent on it, right? The other one is tunable, you can get to it by experiment, that's a different business. But if they're, maybe the height and width of something, and they're just correlated, not a causal thing. So you have to look at what people are talking about, they love it. This is a famous book, it's from '83, so McMahon, I'll talk a little bit about what some of his work, because it's part of the metabolism stuff, talking about shapes of organisms. But it's a Scientific American book, there's a number of these, I don't know if they're still doing it, but they're quite beautiful and rich. So, welcome to look at it, but it's from '83. So this is kind of a nice piece. This is, again, if you can see it more easily there, maybe. These are organisms, and they're all drawn to scale, right? So, I mean, accurately. So there's a human in here, who's a kind of a weasel. There's the blue whale, which is very disappointing organism for the people who love dinosaurs, right? Because they don't have the biggest thing. They get a little upset about it. They have to always say it's the biggest, the largest ever land organism. So, a little bit of a blow there. Really, quite huge. So the sequoia, this is the largest tree, it's about 100 meters. So, interesting work being done on why 100 meters. So is it because of some sort of, is it mechanical? Is it a buckling problem? Is it to do with getting water from the ground up? Replying about this. There's some really nice work that just came out by Aaron Clarsett, who I'll mention a few times here, where it's based on what water is really, and the temperature and so on, and you have to be able to keep yourself warm, right? So fish are very different things. Whales in particular are extremely different things. So a lot of blubber involved with this, and it has this kind of result that the chance of getting a blue whale for the scale of the Earth is pretty high. It's pretty good. So it's not an anomaly. There was a chance of evolving a bigger one. This is just sort of fun things. And the shapes of fish, of course, have some universality to them. I mean, if you want to go fast, it's good looking planes. So these are all the biggest of various kinds of things, right? So we've got a crocodile, which is a good way to get eaten if you're up north of Australia. Usually one person a year, and they're always drunk in a boat. And then they're not in a boat. Crocodiles are very lazy. It's best if you just walk straight into the mouth. They like that. Lots of things. So that's a fun thing. Where Komodo dragon is in there. I think they must have, this must be the elephant bird from Madagascar. I think it is. That was a big image. There's the moa from New Zealand, we got rid of that one, well done. So there's a medium-sized things, so these are kind of the smaller ones, you can see, frogs and so on, large things. And we get down to things that are microscopic. This is kind of a, the point is that there are things at all scales, right, as you know. And it's just kind of an interesting thing to reflect on. So the smallest snail, the smallest frog, what else do we have? And then we get down to stuff you can still see with the naked eye. Another interesting point here. So these are the scales. So we have, this is down to 10 to the minus, what's that range? It's 10 to, it goes up to 10 to the 8. Down to 10 to the minus. So it's just a ridiculous range of scales. I mean, this is the story of life, right? So we have 20, in fact I can't quite say this, but 20 orders of magnitude at least. I mean, that's a massive range. It's a massive range. It's bigger than what we have for earthquakes. All these other things that we look at have many different scales. Life is ridiculously distributed across mass. So, mass scales. And you can measure volume and so on. But let's take mass. That's a profoundly enormous range. This is then the number of distinct, this is interesting, number of distinct cell types as a function of the volume, performance volume in this case, of organisms. So it's there's not really, you can call this really scaling, it's very slow, right? So when we get into a whale, we have about 100 different types of cells, distinct cells that do things. We're down here with one, the bacterial, and it takes a while to get out. But I mean, we're still down at kelp and sponge and these guys, right? So these guys are around at, this is 10, so they take a little while. And then the sequoia is here. So that, that's another aspect, it's another great problem. But all, mammals are made out of mammalian cells. So mammals themselves go from, say, 3 grams to 3,000 kilograms. Yeah, right. So, roughly say for an elephant, right? So then you have, again, 6 orders of magnitude just for mammals, right? Birds have a range is not quite as big. And we'll talk about that. So here's another kind of allometry. It's a little disturbing, right? If a baby walked in and was 6'1 3/4", which is the next one might be, it would be wrong. It would be just flat out wrong. We're totally happy with the baby being a baby. That'll make sense. You know, brains are like, yes, this is a baby. If you scale the person, then it's just yeah. So start up with a big brain and pretty much no ability to do anything. I've been reading my journal from 10 years ago. My first one was about 6 months old. Very different person then. So it's fun for them too. Anyway, so that's a funny piece of allometry, right? Wow. This is a kind of a break-in scaling story, right? We've seen some of this before. This is the growth of arm length, actually, right, with body height. So this is another good example of these correlated ones. So the slope is a bit higher, right? This is body height. So we're getting up to only 2 feet here. But it grows relatively fast. It grows super linearly because you start off with the big head and filling the limbs, and then it starts to taper off to growing linearly eventually, right? When we get to something that begins to look like a bigger human. All right. So there's tons of good stuff. This is an interesting one. So this is the world record. Again, this is in 1993. Yeah, well, it's definitely in the era of massive amounts of drugs, right? At least in the solve some problems in that respect. Honestly, I guess. So this is the log of the body weight of the lifter, right? So we lift the world record, and this is the world record weight. I think it's that was the snatch plus whatever it is. The grunting and all that sort of stuff, but it goes like massively 2/3. 2/3. That's beautiful, beautiful fact. So 2/3, and you think, okay, well, so the argument, again, one of these little background is the sort of a cross-sectional area that maybe as you go across different organisms, you have changes in shape that are allometric, but if you go within organisms, you tend to have relatively isometric changes, right? So these are, this lifter here, you can scale them up and scale them up and scale them up, and they're growing in an isometric way, so their cross-sections are growing to isometrically, and if power is connected to cross-section rather than anything to do with height, then there's a 2/3. So that's the idea for that. But it's not a bad scale. There are lots of others like this. There are world records for rowing. A nice little problem for you there. If you have 1, 2, 4, 8 people in the boat, how does the time scale? Lots of context. There's a paper in Nature a few years ago about the eventual world records. Well, not even eventual, because it was a linear interpolation for the 100 meters. And they had women eventually running faster than men. Unfortunately, it was a linear interpolation. So the problem with that is that, timey-wimey stuff, right, gets a little bad because eventually you go to 0 and then negative time. So we'll see. People love those kinds of pictures. So this is a whole size. I mean, this is a very. So the skulls are definitely getting bigger. This is the length, typical length of the skull here, and this is a very, very rough estimate. I've got GBs. Drawing a line through that one. I'm not sure about the argument for that, but so this seems to be true. So these are, in a sense, naturally made nails, right? People have been making nails for a long time. They didn't just sort of build a factory. The nails came out, and they didn't have that CAD design program or something. They just made nails, right? And a little iron thing or whatever. And so you don't want to make it too. You want your nail to work. It needs to do a job. It's got to be. If you want one of this length to hold something together, you don't want it to be too thick. You don't want to be too thin because it will buckle. And you might also be. You don't want to spend. You don't want to waste money as well. So you want one that's functional. But certainly nails are kind of made so that they're just on that edge of. Right. You have to be careful with nails. So these guys kind of look the same, but if you scale them down. This nail down here, if you scale it up in length, it's not all the same. So in fact, what's happening is diameter is proportional to length to the 2/3. So that's it. We have to think about what that means. But yeah. So length times diameter squared has to grow as volume. All right. So if we replace diameter as growing as length to the 2/3, let's do that. Let's do that so I feel better about myself. So length times diameter squared, so this is volume is proportional to this. The observation is the diameter is growing as length to the 2/3. So this is growing as length to the 2/3 squared. So, seems a little wrong to me. Maybe I have a mistake in this slide. So this is length to the 4/7, 4/3 plus, so 1 plus 4/3, right? I like that a little. So that's going to be 7/3. Now, that seems a little optimistic, because then you'd have, so I'll have to fix this up, I think I messed that up. This would be length is proportional to volume to the 3/7, and therefore the diameter is proportional to the volume, because you need both of them to work together, so it's 2/7. So that means they're getting skinny as they grow up. Yeah, I don't know about that. I think that's not right. I think this is really what we want. So the diameter is growing as 3/8. I think that's right. And then it should be 3/8. I think it should be 3/8. So length is then proportional to mass. Sorry. Current thing at the top. So then length is proportional to mass to the quarter. Yeah, because these things have to fit together, because you have 3/8 plus 3/8 plus a quarter gives you 1. No, it's a little totally wrong. All right, I'll have to fix this up. Lots of lines. Okay. I'll come back and fix it up. So then it would be, here's how this should be explained. Let's see if we get the right thing. Okay, so if this is incorrect, and this is correct, let's see how this works. Again, little just so story. There's a lot of work that gets to this, though, that's quite serious. So columns buckle under a load, which is a good, nice columns made of the same stuff, which are proportional to the diameter of the fourth divided by length squared. It's a whole other area of work to get to. Then there's this little piece that they throw in. So if you want to drive a nail in, the resistance is proportional to the diameter, which you might imagine. Initially, fair enough, maybe, yeah. You'd think it might get a little harder, but that's the statement, so it's going to be proportional to D. And then you want to match those forces, right? So the buckling force is right at that edge. Right? Because if it's any more, then you've made this nail too strong, you're kind of wasting things. If it's too little, then it's going to buckle. And that's going to lead to this. Yeah, it is. Okay. Yeah, so maybe it's this. Okay. So it's a bit different to trees. I think, so trees have this. There's a claim that trees have this one. This is a tree story. I'm going to look. Maybe it's a lie. Actually, it goes back a long way, right? So you have the thing about the buckling thing. Galileo made a story about this. Some links for you there. Well, I got excited about it when he wasn't doing ridiculous series and so on. Yeah. And then there's McMahon has this paper about actually appearing in Science, so separate to this book that I've been talking about that appeared 10 years later. Okay, rowing, I did mention this. So here it is, right? So this is the speed is proportional to the number of rows to a ninth. And there's an argument for this, and I'll give you a little easy question to work on for that. That's a very weak scaling, but there is kind of a fluid dynamics kind of story for how that might work. There's the resistance of the shell and how that might work. Very good. But again, world records, right? Alright. So we've seen all the zip stuff, there's tons of zip stuff. There's more going back in time. This is 56. If you want to look at this, this is sort of a famous piece here. Right. There you go. And this is the right kind of words, right? Principle of allometry, and biological, and social sciences. So lots of examples. Alright. I did mention the Betancourt thing. I gave a bit of a poke for that ridiculous walk. But it's a much bigger piece. So it's about, as it says, growth and innovation, scaling, right? It does have the pace of life title. Which is fair enough. Okay, aside from the walking thing, the pace of life could be measured by crime, disease, wealth, right? These social things. The creativity, which would be measured through patterns. One could measure it through patterns. So this is what they did. Okay, they went through all of it, and I'll show you more. But they're looking just at a function of city size, which is an interesting thing to do. And you have to worry about whether it's the city that they're talking about. They looked across many different countries. And, you know, look, it's a data thing, and I think this is not too bad. So the beta here, if you can see it, is the scaling exponent they measured. So we have, again, this is this ridiculous log thing. This is total wages, right? So that's growing super linearly. So bigger cities, more money. It's not talking about the inequality maybe that it could be in cities. It's talking about the total. This is, what's that one here? That's super creative employment. So that's a funny thing I mentioned there. But it's 1.15. Again, super linear. This is this walking speed thing, which is the dubious. This is a claim. Well, this is generally true. This is the, and we'll come back to it. This is the heart rate of organisms. The resting heart rate of organisms is a function of size. So it goes down, right? Mice, elephants, wandering around. So it's sort of a different plot. Point being here, you know, the observation here is that very opposite things are happening, or it's very weak, but the opposite things are happening. You might think of this as more evidence for that. Okay, so here's the summary. And there are 3 different sections, right? So these are social type things. And this has been debated, and it's not perfect, but this is patents, inventors, with lots of R&D, there's wages, so this is money, GDP. These are in different places, so there's US, China, Germany, right, I think that's it. Different cities, of course, across those places. And there's disease, so there's actually just AIDS cases, there's a disease measure here. Total electrical consumption and serious crime. So these are, electrical consumption is a bit hard to see, but this is sort of very much social aspects to these. Then there's total housing. So total housing should scale as, it should probably scale proportional to people, right? It can't be that it scales in a crazy way, right? You'd have to be sticky, right? You need, eventually you'd have, you know, either no one in houses or, you know, thousands of people in one house, right? It has to be somewhat linear. Even though, you know, you might have more people in buildings and so on, but it can't go out of control. Total employment, household, so this is, right, so there's something else going on outside of households. Of course, there's the companies and organizations. This is consumption here. So this is total consumption of electrical consumption. These are 2 different places. And this is water consumption. So these are all scaling, the claim is, linearly. Right? These things are growing with the city. Fair statement. Reasonable. But then, there are some aspects, though, where you get returns to scale. So gasoline, petrol stations, and sales, the length of cabling in the city, and the road surface. Right? So there's those things are scaling sublinearly. So, you know, if you want to, you double your city size, this is better. You think this is good. You think some of this is very good, serious crimes, these things are bad, right? But they're social in nature. These things you can't do much about, right? Fair enough. I mean, you don't want to somehow mess with housing, but they're reasonable things to be linear. So that's the summary, that you have the sublinear for supply type aspects of the city, right? Cabling, gasoline. And then these individual costs just add up. And then there's some of these, a number of social quantities seem to scale super linear. So it's hard to know what to do. You then build a huge, you just make one big giant city for with the earth and put everyone in it, or and then really work on the disease part. But this is a funny thing. I don't quite understand why this isn't an issue. As I said before, density can vary by 2 orders of magnitude across population scales around the world. And the claim is that it doesn't matter. You'd think that would matter. Right? And the density profiles of cities are very different. Right? So New York City is very much like this, right? It's Connecticut, New Jersey, eventually out here, right? And LA is pretty flat. Right? New York, people come into New York. There is a sensuality, actually, and there is a subway and stuff. But and there is a sense, but people go to lots. It's very spread out. Like a Star Wars movie situation. All right. Okay. All right. So lots, and there are many, many other areas. So there's this is a funny claim. And if you look at the original paper, it's incredibly messy. I think it was MacArthur. It's incredibly messy. But the number of distinct species, very hard thing to measure. Supposedly, and it's reasonable to grow with the area. But there's a idea that it grows as a power of a quarter if we look across islands, in a somewhat co-located area. And if we look at a continuous land and we take a little box and we make that box bigger and bigger and bigger, then it scales as 1/8, which is very bleak. We're going to get into this more and more, but we'll get into one great example of this. But this quarter, I should get this plot. That's what I will do. I'll get that plot. Right, there's a cloud of points and there's a line through it, and you say, well, that's kind of like a quarter, right? And the point was, it increases, but it's not linear, it's not superlinear, it's kind of slow. And so then you have papers appearing in physical review letters 30 years later, 40 years later, where there's a little model making exactly like a quarter. So there's a crystallization that happens as it gets transferred across. Anyway, that's sitting in technicals. All right, Truthicide. So slide rule will matter, unfortunately. All right, so I was trying to amuse myself, but basically, yes. Right, scientific integrity system known as peer review. People are represented by 2 highly overlapping yet equally important groups: the independent scientists who review papers and the scientists who punish those who publish garbage. This is one of those stories. All right, so it's not quite, we haven't quite got to the end of the class, but all right, so funny thing, metabolism, right? Okay. I don't know what you think about this if you come to it fresh, right? I told you a few of these stories already, but here's this idea. Basically, so you get an organism resting, it's watching TV, with some sheep. And you have a shrew, it's watching shrew TV. So it's chilling out, and you measure what's its wattage situation, right? Yeah? It's not running as fast as it can, none of those things, it's just chilling out. So there are some funny ways that this has been measured. It's been measured for at least 100 years, maybe actually measured 130 or 40 years, so it's going back to that time. And I'll go through some of that history. How much organisms eat, for example, you hook up a thing to see how much oxygen they're using, you can do those sorts of things. Maybe you starve them a little bit to make sure they're kind of chilled out. Right? So there's some funny stories. All right, so here are for land animals as we have them now. Here's our shrew, which is not a very big unit, and we're up here, so 6 orders of magnitude bigger. And what we're interested in is this connection between how much energy these things require to run. Right? So we have the story for cities, right? We have the gasoline for cities, and so on. Yeah. That's actually what we'll see. It seems like a biology thing. As you just dial up through mass, it's a big deal, right? So as you dial through mass, it will be bad if it was super linear, because that means we're just going to run out. We're going to get to frogs and I don't know, a couple of rodents and that. But yeah, it's just too hard to run the big systems. Gravity obviously becomes a bit of an issue later on, right? So there's that as well. That's another kappa on how big things can be. But this is the big piece, organismal mass. Right? So we take all organisms of a certain mass, You think about them in different species and so on. But let's see how that works. And so this is an elephant shrew, which is a very bad thing that happened in nature. Very unlikely. So let's see. So we have this. We're interested in this scaling relationship. There is a prefactor that will matter a little bit, and I'll mention it to start with. But it's the scaling of this, so it's resting basal, right? Resting is basal, metabolic rate. It seems that if you get organisms run as fast, you put them on shrew treadmills, and you put them on elephant treadmills, and you put something in front of them that makes them run, or something behind them that makes them run, then they'll scale like mass. It scales like mass. You get everything involved, right? The fastest power output you get. The largest amount of power you can put out scales with mass as you go through organisms. Single. Okay, so, but we're not worried about that. We're worried about just what's the resting thing. There's a lot of resting going on. We rest maybe a third of the day. Cats are, you do the 20 hours limit. Shrews, probably a lot. Obviously, the sloth has got it completely sorted out. And they're going to win because they're cute, right? They're just totally winning. Okay, sloths will be saved. So this prefactorable matter, and it's a nice thing. So the prefactorable matter, in that it depends on the body plan. So we're going to look across mammals and birds in particular. It's a bit difficult when you get to reptiles, right? These guys are going to keep their body heat the same. And there are some rodents there are some mammals where their temperature goes up and down. I think it's our friend the naked mole rat that has a lot of temperature variation. Always worth watching some YouTube videos of naked mole rats. So let's see. So birds run the highest temperature. These guys evolved. We were running around underneath dinosaurs, and then dinosaurs became birds. Very confusing. Or they were just made. I'm not sure. Okay, so but they seem to run. They've got a big job, right? They're doing something crazy. They can fly around. Right? We're pretty much 2D things that walk around the ground. So they run at a higher temperature. Marsupials, so I'm very excited about this part, right? So marsupials, a bit lower down, we're placental or eutherian mammals, right? We've got the whole baby thing on the inside. Marsupials, they stick them in a pouch, right? So you put them in your pocket, which is kind of extraordinary. I mean, when I was a kid growing up in Australia, right, you'd have to see movies of kangaroos and beat the whole, how it works. And this little, tiny little embryo just figures out that it has to climb up and get into the pouch. And then they're good, right? So all these things have pouches. A little front pocket, kind of like overalls, right? And these ones, so of course there are kangaroos of all sizes. That's an important thing. Like there's the Simpson hopping mouse, and then the big reds and that. And you give them food if they want it. So whatever they want, and then the monotremes, the great monotremes, of which there are 2 basic types, and then there are 2 species here, and one of this, so the excellent platypus and the echidna, right? So these guys are on the same page because they both lay eggs. So this is a very different set, right? So we can, maybe this is connected to this, right? So these guys are laying eggs. I know those lay eggs. But these guys are laying eggs within the mammal story. These ones are putting them in a pocket. These ones are, kind of got the oven story going on. So, incredibly, these 2 things are related, which makes no sense whatsoever. It's pretty much a proof against intelligent design. Well, I mean, it could be just unintelligent design, I suppose. That would work too. Anyway, yeah, great things. Beef, the whole, right, good. Echidnas are very cute. Yeah. They tend to do the porcupine thing, which is like, so like, bite me, like, they don't really run very fast. They don't have to. Alright, so those guys lay eggs, they've got pretty low temperatures. And maybe that's all wrong, but we'll see. So, this is what you'd expect if you think about this scale. And I think I can get to, the story of where it all goes wrong. So just dimensional analysis, right? So we're sitting here, we want to keep the same temperature. We're losing heat through our surface, right? That's why the guys with the goggles can find you at night when you're trying to run away, because of the infrared thing. Yeah. I mean, we sweat, yes, that's a big deal. And that really comes into play when we're running around in reflection. And then, when we're at rest, we give off a good amount of radiation. So what are these? It's the so-called black body law, right? Stefan Boltzmann. So if that's true, then, and we're talking about things growing isometrically, another assumption, is an elephant like a shrew, essentially, just a little bit bigger and bigger and bigger. Are they somehow getting wider or thinner? We'll have to think about that one. Gravity is obviously an issue there. So this is assuming, as I said, isometric scaling, right? Doesn't mean spherical cows. That's what physicists do that, right? Physicists assume spherical cows. Okay, so it doesn't mean that. It could be, hot dog shaped cows. It's just that when you scale them, they're all the same. Ellipsoid. Assume an ellipsoid cow with some legs again. Then you think maybe you'd have what we'll call them log normal fluctuations, right? So we're kind of in a log space world. So if we have Gaussian fluctuations in log space, then that's log normal fluctuations. You know about log normal, so fair enough, right? Should be some variations, that's fine. And then this connects here. It's a Stefan Boltzmann law, and so this is the power, how much has been given off. So you have to balance this proportional to surface area. So that connects all these things together. It's radiation. You're a thing, radiation. So that's what you'd expect. And so this is the simplest story. And in fact, that's not what people have come to believe. So the Church of Quarterology would have you believe it's 3/4. So it's a little more, it's a 12th. The Judas number. So 1 in 12 is bad. So this is strange. So why is this? So this is a great mystery. And I have to take you through the history of this. It starts in the 1830s and 40s. And we have to see how this thing got to this stage. But we have beautiful theories. Beautiful doesn't mean right. Beautiful theories from about 15 years ago. And this is a kind of raging debate now. So that's not a big thing. 112. Well, there are a couple of issues with it. First of all, before I say this, it does matter. 12th is not much, but it does matter, right? So if you think about toxicology, well, of course, it's just basic science, so we know what we're talking about. Then there's things like toxicology or medicine, right? So you do things with mice, and then you want to scale up to people. How do you scale up dosage sizes? So, and so the people in government toxicology labs, I know, are quite interested in all this. And so, for this, the higher it is, the more it does point to some kind of inefficiency. I mean, you could say there's something spectacular like usage of energy, but we want to be the sloth approach, right? We want the principle of least effort, the Homer Simpson approach to biological evolution. Evolution has an element of optimization to it. It's not a perfectly optimizing thing, of course, because we end up with a platypus, right? And there's no sense of great, we're not producing paragons of organisms, but they're pretty good, they can do things. They're the ones that are still here. They didn't get eaten, right? So there's a lot of luck and so on, but they're, it's a mix. It's evolution is trying to, keep things around. So there's not perfect optimization, which physicists kind of love, right? So you're trying to get a lot of things to work with the big story of being around tomorrow. But this is an inefficiency, right? So if you're making bigger and bigger organisms, getting bigger and bigger organisms, and they have to scale, their basal metabolism has to scale 3/4. You have to run, they're running hard, right? So it's running hard. And they're doing something else, just more than just balancing heat-bombs, right? Maybe there's something else going on. But then somehow there's a basic inefficiency. So this is not really ever talked about. It's talked about as sort of a magical scaling. But this is something that it's a work, right? But we didn't get it right. Or nature has there's some limit. Something's not tallying out properly. And it's bad, right? Whatever it is, it's you might have some beautiful story for it, but it's kind of a bad thing. Okay. So lots of other things scale, right? So we've just had this basal metabolism scaling mass to some power. It's definitely just something maybe. There are lots of statements like this: number of capillaries or capillaries, whatever makes it matter. Mass to 3/4. Time to reproductive maturity, which is complicated, right? Because this lifespan is very different, right? You can have a cockatoo that's 120 years old and knows what your great-great-grandfather said, fits of rage. But that's it, turtles, you know, they live. But this is, reproductive maturity is a different thing to measure. So here's a nice one. Heart rate, mass minus a quarter. And I'll connect that to in a second. Things like cross-sectional area of aorta. So these kind of all fit together, right? So you're pumping this blood in. Population density. This is a very nice one. Wow, I have to get that one. This is work by Damath a while back. If this mass and 3/4 stuff all fits together, then you have this nice story that all the mice are using the same amount of energy in total as the elephants. Right, so this is so it's a feel-good story. Right? Yeah, it's not like the big guys are, you know, there are less of them, they have bigger ranges, it all balances out. So here's a nice, beautiful story, right? But let's just say we don't really care what the scaling is exactly right now, but if the lifespan is scaling as mass to some power beta, then there's this claim that it's, you see, oh, Radio Lab loves this one. I mean, you'll see people love this, people write poems about it. Average heart rate is going down as mass to minus beta. Then you have this very nice thing. So you have to multiply these two guys together, right? So the average lifespan times the average heart rate to give the total average number of heartbeats in the lifespan, providing you don't get run over by buses, right? I mean, so it's mass to the zero. So that's a beautiful idea, right? So it's independent of organism size. People love this one. You know, it may not be entirely untrue, right? I mean, so there's this notion that elephants' hearts beat slower, boom, boom, right? And they get the same number of heartbeats as a shrew that's hammering through existence. Sees everything in slow motion, right? That's, you know, and so that's a beautiful idea, and maybe that does hold true. I don't think it, even if it varies a bit, it's not completely out of control. So it's not as if an elephant has 100 times more heartbeats in its life than a shrew, or 1,000 times more, or 10,000 times more. It's, you know, on the order of it. All right, so, and 1.5 billion is kind of a rough estimate. So what do you do, right? You train, make it go harder, so it's lower, and the rest of the people love that one. Yeah. I've sat on the couch my whole life. So. Or you go running, you're shortening your life because you're using up heartbeats. But, yeah. All right, so we'll get to death by fractions on Thursday. I'll take you through the history of where this came from and the great theories of words. Why 2/3, why 3/4. I'll tell you where we are. All right. Okay.